Hello everybody and welcome back. In this video solution, let's talk about the problem perfect squares. We're given a single number num and we want to break it down in such a way that we want to return the number of numbers which are perfect square numbers which can be used to break this number down, and the sum is equal to num itself. It's a bit complicated, so let's actually try to look at a sample case. In the case of 12, which is the number given to us, we want to break it down into sum of perfect squares. So it could be something like 2 squared plus 2 squared plus 2 squared. So this is 4, 4, 4. 4 is a 12. One other possible way is to break it down as 3 squared plus 1 squared plus 1 squared plus 1 squared. This also gives us 12. Now the goal of this problem is to return the minimum possible number of numbers required to break this number down. In this case, the result is 3, and in this case the result is 4. Since 3 is lesser than 4, we will return 3 for the case of 12. We'll explore this case later on because this is the most interesting case, but first we want to try to formalize what we have already. The thing is, we want to break this particular number down into a bunch of numbers, right? So what we're trying to do is we are saying number can be broken down as a times 1 squared, b times 2 squared, plus c times 3 squared, and so on and so forth. Right? This is the way we are trying to break down all of these numbers, all of these num, and I'm going to write alpha times x squared as the maximum possible value it can have. Now, the thing is, we want to minimize the sum of all of these coefficients, a plus b plus c, all the way up till alpha. This is the goal of this problem. But this is a bit complicated. I mean, first of all, what is this alpha and what is this x? We should try to answer this question so that maybe we can limit how far we have to search. So we're starting from 1 and we're going all the way up till x. And so we want to sort of restrict the ranges of what x could be. So like we're going to look at a purely mathematical approach. Let's say that num is just equals to some coefficient of x squared. What is the maximum possible value of x? That is the question we have. And if you look at it, it's very simple. We can just write x as the square root of the number itself. I'm going to write it as n from now on. And this is, of course, it could be a floating point value, so we'll have to convert that into an integer. And this is going to tell us the maximum possible value of this x. Because in this way, we are sort of restricting how far we have to search. Like we are starting from 1 and the 1 is fixed always, but we're also trying to find out this ending position, this x value, where we have to stop our search. So this sort of simplifies our assumptions a lot. Okay, so we have found out x now. And in this way, we can sort of now take a look at another example and we'll start to break it down again. So let's take another example. Instead of 12, we'll take 120 say, and I want to break down this number. The first question we'll ask is, okay, what is the x going to be? What is the maximum possible value, the maximum possible integer value of the square root of this guy? That is going to be 10.95 in floating point, something like that. And so we can just write it as 10. So we know that x is 10, which means that we can write the number 120 as 10 square plus some remainder. This we can easily mathematically compute, which is going to be 20. Now the thing is, we have broken this down into 1 square and this other leftover number. Can we not do the same computation again? Sorry, let me write it this way. Can we not write 20 equals to some numbers squared plus remainder? In the case of 20, the x is going to be, I mean, basically you can do this manually too. So you can just say x equals to 4 at maximum, which means that we can have 4 over here. So 4 square 16 and the remainder is 4. How can we break down 4 again? Right, we can just take this guy over here and we can again do the same computation. In this case is 2 square plus 0. So you can see how in 3 steps how in 3 total steps we were able to break this 120 number down into multiple different pieces. Final answer being 10 squared plus 4 squared plus 2 squared. 4 squared plus 2 squared. And so these are the 3 numbers and we've got the final answer. Pretty cool, right? We could just find out this x guy and we could just continue to break it down further and further. Now I want to come back to the original question we had, which is the question of 12, right? 12 was the number we wanted to break down. Now let's try to do that again. So what is the maximum square we can write over here? If you again do this computation of finding x, that is going to be 3 in this case. So we can write it as 3 squared plus the remainder of 3. Correct? We can now again move it over here. So 3 equals to 1 squared plus 2. Similarly, 2 equals to 1 squared plus 1. And finally, 1 equals to 1 squared plus 0. This is where we end. And now we can finally compute the answer for this guy as 4. 4 looks incorrect. Let me actually show you. The answer for this case wasn't actually 4. It wasn't actually 3 squared plus 3 times 1 squared. It was actually 2 squared plus 2 squared plus 2 squared, because that gave us the lesser answer of 3. How do we include this? It's clear that, we were trying to greedily find the biggest possible x and we were trying to break it down like that. But it looks like x equals to 3 is incomplete. So we also need a way to say that, 12 can also be broken down as to 2 squared plus remainder. And we can do the same computation again and again and again. So we need a way to say that, maybe 3 is the answer, maybe 2 is the answer. We don't know for sure right now. When you are at this first iteration, when you are looking at this breaking down of it into 3 squared and 2 squared, at that point you can never say which of them is going to give you the better answer. You have to somehow look into the future of how this remainder value plays out in the future. Like, you want to somehow look into the future. And if you have been following my channel for a while now, you'll realize that this is the cue for recursion. You can just use a recursion and we can break this problem down. So I just want to quickly demonstrate how we can actually write this in terms of recursion. And we can then directly jump into the code for this part. So what we are trying to do is we're trying to say, 12 can go to 2 different paths. It can go to 3 or 2. I mean, technically it can also go to 1, right? We aren't restricting it to be 3 or 2. It can also be 1. Maybe it is 1. I don't know. So 3 will give me 3 squared, which is 9. And so I'll have the remainder as 3 over here. This is going to give me the remainder as 8. And this is going to give me the remainder as 11. Similarly, I can do this again. So how can I break down 3? I cannot use 2. I have to use 1 over here. So I'll go to 2. And then again, I'll look at 2. I have to do 1 squared. So 1 and then finally 0. Similarly, in this case, we have 8 over here. So I can either use 2 or I can also use 1. Right? I have 2 different options. So I'll go ahead and reduce 2 squared, which gives me 4. And I'll reduce 1 squared, which is 7. Again, I have the options of 2 and 1. So this gives me, in this case, it will give me 0. And in this case, it will give me 3. And so on and so forth. You can basically do it for every single case. Now, there's one more thing that I want to demonstrate very quickly. If you look at it closely, this 3 value is being repeated over here. There's somehow overlapping sub-problems. If we have computed this chain of values, then we don't need to compute this again for here. We can just copy paste this guy, right? Okay, cool. I think we're pretty much done with all of the basic things we needed to get set up. So we can finally start to code this guy up. The first thing we want to do is we want to have this recursive kind of structure, right? So I'm going to call this function dp, and it's going to take the input as n, the value we're looking at. So in this case, we initially started off with 12. In this case, it was the value 3. In this case, it was 8, so on and so forth. We only have one single value that we need to input. Okay, what are we having this dp function return? That is also something we want to get clear on, because okay, what are we trying to return at this point? So if I look at this particular value, I want to make a decision whether to go this side, whether to go this side, or whether to go this side. And how can I decide which way to go? Well, what was the goal of the problem? The goal of the problem was to say that the sum was equals to num. Okay, that's something we have found out. And we had to minimize this number of numbers required. In other words, we were trying to do this depth first search, and we're trying to minimize the depth at which we have to go. So it makes sense for us to return the length or the depth of this entire search. In this case, it's going to be 4. In this case, it's going to be 3. And in this case, it's going to be some other value. And so we can finally say that this is the best possible path, this one. Okay, we have made enough mess over here. Let's try to formalize this. We are trying to return the counts at each point. Okay. So what is the base case? The base case is when n equals to 0. As we saw in this case, we have this 0 as a remainder over here. And at that point, we were satisfied. We were able to successfully break down the original number into its little different components. So if n equals to 0, I want you to return some count. What is that count going to be? I'm going to have it return count 0, because from the point 0, you have to take 0 steps forward to get to 0, right? Like that's the base case. Sounds kind of dumb, but that is it. Okay, since we also want to minimize the count, let's go ahead and initialize that to infinity, and we'll try to return this count at the end. Now let's come to actual core of recursion. I want to iterate over all of the possible values. So I want to iterate over all the range in 1 to x. Now what is x? I'm going to write x over here as the integer value of the square root of the current number n. And I also want this to be inclusive of x. So it's in the range of 1 to x, both inclusive. If you look at this problem again, I've just made a mess over here, but I'm just going to write it over here. What we have done is we wanted to break down 12. And so I took the square root of it, and x came out as 3. So what all ranges do I want to explore in this case? I want to explore 3, 2, and 1. So anything from 1 all the way up till x is something that I have to explore. And so we'll go ahead and iterate over all of the values to 1 and x plus 1, both inclusive. If you don't do this inclusive thing, by the way, I made this mistake and I had to spend like 15-20 minutes debugging this guy. If you don't do this plus 1, this will cause a wrong answer error. So you have to do x plus 1 over here. Okay. Now that we have the current I in hand, the number we want to result is, it is going to be n into n minus I times I. So I'm trying to reduce I squared from the current n guy, and I'm trying to recurse. So I'm just going to call dp of this guy. And this is of course going to return me some count. And I'm going to say, is this count, is this temporary count better than this count over here? So I'm trying to take the minimum of count and the temporary count. I'm going to store that in count itself. One quick basic check is this value should never go lesser than 0. So I'm just going to check if this value is greater than 0, or I mean greater than equals to 0, it's only then it's okay to count this recursively. So only if it's positive value greater than equals to 0, then we're going to do this count. And with that, we can return dp of n, which is the original number itself. And I'm going to make, I'm going to do LRU cache as none. Let's do a quick sanity check. Okay, invalid syntax. Okay, yeah, I make this mistake a lot. It's very standard. Cool, the answer is 0. Why is the answer 0? All right, I don't actually want to return temp. I want to return temp plus 1, because I looked into the future, okay, how many steps I need to take in the future, but I also have to count the current point of time. So plus 1 because of that. I think this should work. And hopefully this does not give me a time limit error, because this is a very borderline solution. I'm going to explain how we can optimize this a lot, and it's going to be fun. But first, let's hope this works. Ah, damn it. Okay, so we're going to basically cut corners at this point because DFS solution is not really the best for this question. Cool. So as you can see, this is a very borderline solution. Runtime is like very close to 7 seconds, and I'm very sure that this would fail in like every other competitive programming platform website, because DFS is not the right way to look at it. And now I think we can finally jump into the BFS solution. In the BFS approach, all we're going to do is we're going to look at the problem differently. We had this 12 before, and we looked at how to break it into 3 different parts. One was 3, one was 2, and one was 1. And in this way, we were doing 12 minus 3 squared, which would give us the answer 3. 12 minus 2 squared, which was 8. 12 minus 1 squared, which is 11. And from this point, we were trying to explore in more directions. So 3, only 1 is possible. So I'm going to get 2, then 1, and then 0. This is the previous approach. We're trying to do a depth first search. We're trying to see, okay, how long does this go? And then we would store the answer and return it over here as 4, because 4 is the depth of this search. But what we can also do is, instead of going this depth first search, we can look at it breadth first search way. So what I'm going to do is I'm going to look at all of these values instead of 12 now. So this is the first layer, sort of the 12 is the first layer. Then 3, 8, 11 is the second layer. And from 3, 8, 11, I'm again going to take one step forward for all of these guys. So from 3, I'm going to take 1 and I'm going to get 2. 8, I have 2 possible cases, 1 or 2. So 7 or 4. And then for 11, I have 1, 2, 3, all of these cases. So something like that. And then again, I'm going to take this as the next layer and I'm going to continue my computation. In this way, as soon as I get, like, we'll again explore this guy to be 1, this guy to be 1, 2, like something here. But as soon as I hit this case, I'll get the result as 0. By doing breadth first search, we were able to compute the answer more quickly because I did not have to go in this direction all the way. I could just look at it and I could stop because I already have the answer here. As soon as I get one particular 0, just 1 0, I'm going to enter it right here because this is the first 0 I got. So I can be happy and say that I'm cool. In this way, I've taken 1, 2, 3 steps to get here. So I can return the answer as 3. And the answer for this case is indeed 3. And by doing a breadth first search, we're able to cut down on our search space a lot. Right? In DFS, we had to explore a lot. We had to go the entire depth, find out the answer, and maybe that could give us the best answer, maybe not. We still had to go again all of the times searching for the answer. In this case, we're going layer by layer. If this layer doesn't give us the answer, maybe the next will. If this layer doesn't give us the answer, maybe the next will. So on and so forth. So this is a very small sort of tweak in looking at the problem, but it's a big change from DFS to BFS, which is going to make all the difference. Okay, the first thing I want to get set up is with storing the square values, because we want to iterate over this 1 square, 2 square, 3 square thing again and again. So I'm just going to pre-compute them. I'm going to have 1 star 1 for I in range of 1 to x plus 1. X plus 1 is again very important. I cannot stress this enough. Please do x plus 1 and not x. Now I want to do square root of n over here. So we have the x. Now we can finally start to explore like layer by layer. So I'm going to set the explore to be a set. It's not an empty set. It contains the first value n, because 12 is the first guy we're looking at. Okay, so I'm going to say while there is something to explore, do some exploring, and we'll also get set up with this count, which is going to be 0. So while there's something to explore, increase the count by 1, because we are now looking at the next layer instead of the 0th layer. And we're going to do some more computations, but also return count over here. Okay, cool. We can finally focus on this guy. I want to iterate over all of the possible values in this guy. I want to look at all of the possible values that I can explore. So I'll do for x in range of, sorry, for x in just explore. I'm going to look at each of these values, and I'm now going to look at for, let me just call this n and x to be consistent. For x in squares, now I have the axis of n and the x. Now I'm just going to do the same thing again and again. So I'm going to say if n minus x is equals to 0, if by reducing this x from n, you were able to get a remainder of 0, that means it's a good case. Then we have found sort of the ending of the breadth first search, and we can return the count right away. If not, that's still okay. I want you to check if n is greater than x, which means that you can do n minus x, which is greater than 0. Remember the DFS we did check for this. We said that we don't want to search for negative values. That does not make any sense. So only if x is, only after removing x from n, if it's still greater than 0, then I'm going to do temp.add the n minus x value. So we'll also set up this temp, which is going to be a new set. And once we're done with this entire computation, I'm going to set the explore to be the temp. What this is essentially doing is, this is the current explore. Okay, in the first iteration, this is the explore. The next layer that we're trying to form by adding elements to it, like 3, 8, and 11, we're adding these 3, 8, and 11 over here. And at this point of time, this is the temp. What happens in the next iteration? This temp becomes the explore. So now we are at this explore, and now we'll start to form this as the temp. This is the logical layout of the problem. Okay, finally, you can go ahead and submit this, and I'm going to show you the big difference between runtimes. Look at this. This is 374 and that is 6940 milliseconds. Look at the huge amount of difference between depth first search and the breadth first search approaches. Anyways, this is it for the problem perfect squares. If you like this video, give it a thumbs up. If you want to see more daily problems, subscribe. And as always, thanks for watching.